many ways. We can talk about a pirate's booty. Is there, you know, so there's the treasure chest.
Yeah,
no.
pirate's booty.
Yeah.
Does it actually mean?
I swear to God, you can look it up right now.
He's right.
But will the answer UK be?
Booty is the name of the little shoes for infants. A little booty. Yeah, you see, you can slip it in casually.
Yeah.
This is your challenge.
The most two famous sentences in the world: "I love you" and "Made in China," and both have no guarantee.
And look, this guy has both.
No.
I love you, and you're made in China, right?
Both of them together.
Fake.
He's not fake.
You never know.
Steven!
Huh?
Lee used to call a blanket a quilt.
What's the name for it?
Yeah, but who uses it? Like it's
I
all.
took this. No, I'm serious.
Nice.
Yeah.
Where'd you get it?
The floor.
You're evil.
Next to the flower tree. Flower bush. Because I didn't want to pluck a flower out, so I was looking, maybe there was one on the floor and I found one.
Good.
Because I don't kill anything.
You're going to give it to Fuang?
Of course not.
Oh, sorry. Yahya, of course.
He didn't deserve my love.
That's right. He deserves a fate much worse than this.
She rejected me.
Okay.
Oh, I rejected you in front of the whole class. What do you think told us that story?
Is that a story that was told?
Who rejected you? What? I'm so lost.
I don't know what's going on.
No, you know.
No, I don't. I think he's making fun of you, but I'm not certain.
No, not him.
Oh, who?
She was a teacher in a different college. And the guy asked her out and she was engaged. And she rejected him in front of the whole class. Look at me. All the boys want me. But I reject all of them.
What was the name of that teacher?
What? Was a teacher?
Why do you hate him?
Is that a true story?
I want to believe it. Oh, it's a true story that we were told.
Oh. I had my suspicions. Thank you for confirming it.
That is not the first opposite sex story we heard from that teacher.
They're interesting.
I'll have to confirm that. It's so crazy, it just might be true.
Was your name Corinne Polan?
No lane, colon.
That's a doctor to you.
Oh.
Take my apology back.
Okay.
You.
Hey, okay. Just opening the spreadsheet here.
Libre.
So the last thing to look at in maths, really, really short and straightforward. And you kind of looked at it a little bit in physics. Okay, so I'll give you an example. Let's imagine you have an experiment you're doing and you're trying to measure the value of G. And let's say we have, what have we got, 1, 2, 3, 4, 5, 6, 7 different people doing the experiment. So Andrew does the experiment first, and maybe he does it, what?
Yeah. Because you said 7, I'm like, we're 8.
Oh yeah, yeah, where is Yusuf actually?
Doing drugs.
Possibly. He doesn't seem like the type, but you never know.
Telling me this, telling me that.
Right, so, Faisal, please. So, Andrew does the experiment, and he does it 9 times, and he comes up with 9 different values for, what?
He does the experiment 9 times, and every time he gets a different value.
Yes, that's normal.
What is this?
That's, if you did those experiments again, you will not get the same values.
If I do it 9 times, I get one result.
Yes,
Or
I'm
9
not
times.
finished.
Because I am perfect.
Precise.
Consistency.
You finished yet? Okay.
You made the game.
So, Andrew does it here 9 times, 9 different values. And then we go on to Lee, and it's the same story here.
Andrew A, Booty B.
9, 10.
And then the new word, Sean.
Please stop. You good little student, will you? Okay.
What?
He called you little.
I must say so. The
10, 20.
11. Okay, then we go on.
Booty.
Let's see, 9.5. 9 point.
I guess C is yours.
Yeah, and who's
Because it starts with 9 and ends with 11.
Kaboom.
Harsh, do it harsh. 1, 2, 3, 4. Okay, I won't do them all here. I'll just give you enough to give me an idea.
Let's get to us.
Do you know 9 million? You know it very well. I'm just curious, were you there taking photos?
Yeah, where were you on that day actually?
There.
You hesitate too long now. If this was an immigration inspection
underground floor on the building, I pressed the detonator of the TV.
Oh, that's it, right, yes. Because it was a government stitch-up job, wasn't it?
What year was it?
Operation False Flag.
What year was it?
Right! Now,
2001.
yes, 01, correct. Here we imagine that the students did the experiment 5 times. And of course, each one will get a slightly different answer. So the first one,
Should have been 2011.
first one here, get this average. And the second one, this average, and then this one, and then this one, and then this one. So everybody gets a different result. This is normal.
That's a D and the
Oh, sorry, that's way off. Whoever was this person really made a mistake there. Right there, that's a bit better. Right, so each person gets a different result. This is normal. And remember, I said in physics, you want to put some kind of uncertainty to your answer. You remember?
Yeah.
So, a couple of ways to do it. Let's have a look here at, I think it might be this function, no. std.dev.
Name, question.
Yeah, I just have to get the exact name of the function here. Okay. So there. So let's say Andrew did the experiment here and he got a value of 9.7, and this standard deviation is 0.3 of his data. Does anyone remember what the 0.3 means? The standard deviation?
How much it is off by?
Yeah, how much each of his 9 results are off by on average. And for the next person, you get the next value. So if you look at person C, they have, this is a good example, they are the most accurate, it looks like. Correct? They're the most accurate. They got 9.8, and the true value is 9.81. However, they are the least precise, because their answers are different the most.
Who?
C.
Yes.
Yeah.
Because they go from 9 to 11. So they have a huge range of possible answers, but they were the most accurate. They were the most accurate, but they were the least precise.
How most accurate?
Because they're closest to the true G value, 9.81. Aren't they? I don't see anyone else better.
Who? Okay, but you didn't say that we're doing G, so okay.
I'm sure I did at the start when you were making noises or not listening to me or doing both. But
Who else heard him say G?
Maybe they couldn't hear you with all the noises you were making.
Maybe.
Right, just in case. These are doing experiments to calculate G.
Okay.
So C is the most accurate. Who is the least accurate?
But then there are 9.8.
E is the least accurate in total. E is the least accurate. Who is the most precise?
C.
No, the only
No.
least.
D.
D.
Oh, D. Yeah.
These answers differ the least. Okay. But what we really want to know is not the standard deviation within the data, but the standard deviation between the experiments. In other words, I want to know, on average, how much would his results differ from his result on average. So that would be looking at the totals. Here is the average of them all. But more importantly, here's the standard deviation. So what you're saying here is, if you look at everybody's experiment, what was the average result? 9.7. But this 0.05, that's the uncertainty that you did in physics. That's how much, on average, each experiment can differ by. The last lab report you did with Newton, remember you had to calculate the uncertainty of the mass. That's what this is like, the uncertainty of the G. But the problem is, let's imagine that you're Andrew here, which I know is a problem, but just get over that fact first. So you're imagining you're Andrew, and you've done this experiment, and you've gotten this result, and you've gotten this standard deviation. But this is not the standard deviation you want. This is the standard deviation for your data. You want to know how much is the standard deviation between the experiment results, not for within yours. Now, of course, the problem is you can't see this because you only did yours. So the question is there a relationship between this one and this one? That is, if you know this, can you know this? And it seems like, well, you can't, because you would have to know all of these as well. But in fact, believe it or not, there is a relationship. Now, the relationship isn't exactly perfect, and because it's quite small, I might not get it exactly perfect here. But the relationship is, you take your standard deviation, and you divide it by square root n, which in this case is 9. Now that should seem familiar, because remember when you did your calculation in the lab report, do you remember you had to divide by square root n? Yeah? So if you look at that, you get 0.10, which of course is not the same as 0.05, but if we had bigger data, it would be closer. So the end result here is this formula I want to give you called the standard error. How wrong is your experiment? How wrong is your result? And the answer is, it's equal to your standard deviation divided by square root your sample size.
Would we get the same answer if we did it to all the others?
Good question. We should. Let's see what happens. Yeah, not bad. Not bad. Oh, that's much bigger. That one's quite close. And that one again is similar. Yeah. You're right. We should get it roughly the same. But of course we won't, because everyone's a little bit different.
That's what makes the world beautiful.
It is indeed. And some of us are more different, strange, wonderful and weird than others. Yes. Now, how can you use standard error? Well, the way it works is, imagine x is the thing that you're calculating, that you're estimating. So in our example, x was the value of g, 9.81. You want to put boundaries on that estimate. So you would say it's less than and more than x minus and x plus the following simple formula, plus 1.96 standard errors minus 1.96 standard errors. So you think the true answer, which we use this symbol for the true answer, is somewhere between your estimate plus this and your estimate minus this. In other words, this is just like the error, the plus minus error. It's a simple formula, but it's quite accurate. Let's have a look before you can write this down, but let's have a look here. In Andrew's experiment here, he got a standard error of 0.1. So if you were to look at his two ends, he would get this minus 1.96 times the standard error. And then the other one would be plus. Andrew's estimate, does it include 9.81? If you look at his lower and his upper. It does. 9.81 is in there. So if Andrew said, I got a value of 9.7, but it could be between 9.5 and 9.9, he will be right, because the true answer is between those two.
So what's the formula to get that?
It's right here at the bottom. You can write it down in a sec. It must be bigger than this and less than this.
The 1.96 is specific for...
To the formula, correct, yeah. Yeah, it's a constant.
For calculating...
No, for all of these problems, yeah. Let's move this across to person B. Is the true value within their range? Yeah. Here?
They're the same exact values.
Oh, that's because, yeah, funny that. I want my A to change. Yeah, the exact values would make it the same each time, I suppose. Right. Yep. Just about, but still in there. Yep, still in there. So this is a very simple but a very powerful formula for putting errors on your calculations for experiments. This is called a confidence interval.
Well, what is called?
This formula, this idea. So remember, for the Newton experiment, you wanted the true mass to be within the two boundaries you calculated.
What do you mean by estimating that?
Oh yeah, because when you do an experiment, you're trying to estimate the true value of something. So you usually average your data to get the estimate. And that's what you would need.
So it's X is the average.
X at the bar is like, yeah, the average from your data. Just to be clear, guys, this means the estimate from your experiment. This is the average. This means the true value. You can never know the true value, but you can put bounds on it. You're going to smoke them later. Come on.
Gotcha.
Those are technically stones. Pollens.
And you touched them. Ew. Okay. Shall we continue now on to physics or maths? We say physics exam. Yeah, because I mean, I've already, the only example here would be, like I said, it was small. The only example would be like, let's say I did an experiment and I wanted to know the mass of something, an apple. So you do 100 grams and then you do it again, you have 105 grams, 96 grams and 102 grams. So first you get the average. Do you know how to get the average of four numbers?
Oh no.
Yes, add them up and divide by 4. Plus or minus the standard deviation. Good news, because this is not technically on the course, they will not ask you to calculate this. and will give it to you with the data. So they will say something like standard deviation is whatever, 2 grams. Multiplied by 1.96 divided by square root 4. 4 here. That's all.
One goes down.
So here's another quick example. 98, 99, 101, 102. I don't know what the average is. Let's just say, well, maybe we can calculate. It's about 100, isn't it? It is 100, isn't it?
Yeah.
Plus or minus 1.96 times whatever the standard deviation is. It's about 1.4, I'd say. All over square root 4. But note, the exam will give the average and the standard deviation in the question.
Will they give us the formula?
This formula I think is in the formula book. So like I said, there's not much to show you in this lesson.
Or 2 more?
2 mark section A question, yeah. It'd be a 2 mark section A question. Yeah. They usually have it in with the normal distribution question. Yeah, okay, good. Shall we look at the physics paper? Yep. You okay, Flan? Yeah. We look at physics now? It's this sort of X-Man talent to be able to sleep through any situation. No, you can't wake him up. It's a superpower. Ouch. I know, I don't think he's asleep enough. Hello.